Hi guys, we're doing 7F now, and it's a two-part video series, and there'll be 4 examples to show you. And the first one is a semicircle, and the difference between these techniques and all the techniques we've done so far is that we make x a function of u instead of u being a function of x. In this first one, I'm not actually telling you what to use for the substitution, so that once you see this, you'll kind of know what to do if you get something like this. In the second one of part 1 video, we do tell you what to do, okay? Now, all of the examples in your textbook that follow on when you get into your own private work from this exercise, they will tell you what to substitute. But I don't think you're going to get something like that in the exam, the VCAR exam. The recent exam which I'm thinking of had examples of the type of part 2 of the video that I will show you, and they were pretty out there, I'm telling you. Unless you were a little bit astute and not too stressed, you wouldn't really know what to do. So that's why I'm showing you, in case they pull that stunt again, and then you'll be ready for them, okay? So let's do this one. In this example, we're going to make x equals 3 sine u, the 3 being because of the 9 here. It could work equally well if you used cos u, okay? I'll show you why that works in a minute, but basically the 3 is because when you square it, it'll become 9, and this whole term here will collapse into a lovely little peaceful, unharmful little submissive thing which you can work with. I'll show you. It's pretty amazing. Dx du will be 3 cos u, and dx will be 3 cos u du. Now, we've got to change our terminals. So now when we think about this, u is actually the angle whose sine is x over 3, okay? You got that? Yeah, so therefore when x is 0, u will be the angle whose sine is 0, okay? When x is 3, of course, so u is the angle whose sine will be 3 over 3. Now, I need to tell you something here. Just pause your brain for a minute. In order to do these kind of substitutions where you're doing x as a function of u, you need to make u a one-to-one function. So what I should have set up here, and I apologize, I should have said where u is going to go from minus pi on 2 to pi on 2, which is the principal domain for sine that we use when we're defining inverse circular functions, okay? So I'm just going to borrow that same principal domain for sine. Then we've got a one-to-one function, and that'll all work fine. Now, the reason I'm mentioning that is when you get this down here, when x is 3, u is inverse sine, or the angle whose sine is 3 over 3, which is 1. The angle whose sine is 1 for that principal domain that we just chose is just pi on 2. Okay, so now we've got our terminals changed to u terminals, and I've got this expression here under the square root sign, which if you just think about it, feast your eyes upon it, you'll work out what to do and why I made that thing 3 sine u, and it would work equally well with 3 cos u, by the way, and I want you, when you finish looking at this, to try it with 3 cos u and prove it to yourself that it does work, okay? Okay, now dx is all this beast over here. Pretty crazy, see? Look, dx is 3 cos u du. Now we're going to collapse all this. Take the 9 out as a common factor, and you'll get 9 times 1 minus sine squared u. And of course, you know what 1 minus sine squared u is, don't you? Yes, it's cos squared u. And then we've got the positive square root of 9 into 1 minus sine squared u, which basically is just going to be 3 cos u. Look at it. Amazing. Yeah, truly amazing. So don't you reckon that's devilishly cunning? It definitely is devilishly cunning. So now we're left with this, okay? That's your square rooty thing becomes that, and there's your du, which becomes that. So what have we got? We've got the integral of 9 cos squared u with respect to u, and then from 0 to pi on 2, and of course you know we're going to use the even technique, so that becomes that thing in there becomes a half of 1 plus cos 2u, and I've put the half out there, and that's very easy to integrate, isn't it? 9 over 2 times u plus a half of sine 2u between 0 and pi on 2. Now, do I need to move? Yes, I probably do. Just a minute, and I'll just move myself. Now, what I've got in here is from the upper terminal. So that's 9 over 2 times pi over 2 plus a half sine of pi, because 2 times pi on 2 is pi, and of course sine of pi is 0. And from the lower terminal we get minus 9 over 2, and there's a nothing there and a nothing there, so that just doesn't give us anything at all. So what I'm getting for my answer, guys and gals, is 9 pi over 4, which makes perfect sense, because remember I said we're working out the area of the upper right hand quadrant, quadrant 1 of this semicircle, which is sitting above the x-axis and symmetrical about the y-axis of radius 3. So what, come on, you tell me, what's the area of a circle of radius 3? Pi times 3 squared, isn't it? So that's 9 pi, and this is a quarter of it. Ba-doomch! Don't you love it? So now, what I want you to do when you're ready is pause this, or later on if you like, do the whole thing with x equal to 3 cos u, and prove it to yourself. It does actually work, all right? So well done. All right, over the screen we go. Now, this is another example of the same kind of substitution where you make x equal a function of u, except in this one, they're telling us what to substitute, and all of your textbook exercises will tell you what to do just to give you the practice. But remember, I don't think VCAR is going to be that kind to you guys. You know, we know about VCAR, don't we? So therefore, we will do this, and then we'll go to part 2 where you'll see the wobbly ones that you're more likely to get from VCAR with no hint at all what to do. Now, this one, okay, so what are we doing? We're told that x is tan u, therefore dx du would be sec squared u, and therefore dx would be sec squared u du. And then we've got to unravel what all this stuff is in terms of u, and you'll notice there's no terminals here, so we don't have to worry about that. Okay, so if 1 plus x squared is 1 plus tan squared u, well, that's going to be the same as sec squared u. And therefore, the denominator is 1 plus x squared all squared, which we would get sec to the 4u. Good grief. Okay, now where does that leave us? By the way, you'll notice that we've been told here that u has to go from minus pi on 2 to pi on 2, which is the principal domain of a 1-to-1 tan function, if you think about it. Yeah, it is. So that's why u has been chosen that way, because you have to do that for this kind of x equal a function of u technique to work, okay? All right, so now where were we? Yes, we got all this. So there's the 2 was already there. The dx is all this, and the u squared, good grief, the 1 plus, no, hang on, what am I saying? The 1 plus x squared all squared became this, didn't it? Yeah, okay, so that's going to cancel nicely. The numerator is going to cancel with the denominator, and we're going to be left with that. And of course, we know 1 over sec squared u is just cos squared u on the denominator, so we get that. Now, see, we're really out of trouble now, guys. We're really out of trouble. We can just use the even technique with great effect to fix this up, yeah? Okay, let's go. So therefore, yes, the cos squared u is just a half of 1 plus cos 2u. These little beasties will cancel out. Nicely done, and we're left with that after we integrate, which is just u plus cos, or half of sine 2u, sorry, plus c, yeah? Now, we need to change this back into x notation, yeah? Oh, goodness. So that's going to look a little bit messy, okay, when we do that. See, look, do you agree? U is the angle whose tan is x, you see? So now, what do we get? Okay, we've got the angle whose tan is x, that's the u bit, plus a half sine of 2 times the angle whose tan is x, which is very messy and quite revolting, plus c. Now, guys and gals, if you were so inclined, you could fiddle with this to make it a little bit nicer and simplify it a bit. And you do that with the magic triangle I'm showing you. I'll show you this. Look, this magic triangle, I'm telling you, is worth its weight in gold. You want to get into the magic triangle. It's great. So we can see here that, as I said, u is the angle whose tan is x. So let's draw that. There's x over 1, and u is the angle whose tan is x over 1. So we can find out the third side here, the Pythagorean side here, the hypotenuse, which would be the square root of 1 plus x squared. Now we can really get into this. Look, see this let's go to this line here instead of all that mess. Sine 2u, okay? Sine 2u, you know from double angle formula is 2 sine u cos u, isn't it? Yeah? Which is going to be, look at that. See, it's 2 times, okay, sine u is x over the square root of that thing. And then cos u is 1 over that thing. And look at that. Just look at it. So this times this just gets that 1 plus x squared without the square root sign. So you end up with 2x over 1 plus x squared. How simple is it? How simple is it? So that's sine 2u. So now we can rewrite our answer as, okay, I'll show you. Yeah, so, oh, I just need to move again. Just excuse me. Yeah, we just got the angle whose tan is x plus, now this sine 2u was 2x over 1 plus x squared. So if we've got a half of sine 2u, it's just x over 1 plus x squared, and then we're adding c for you and me. And that fills us with glee because we just absolutely demolished that question. Okay, so you can go ahead and do those exercises in your textbook now with great aplomb, and I'll see you in part 2 for the VCAR wobbly bit. Okay, all the best.